Here are 11 steps that you can take to design your medical device for more sustainability. So let's get going. My name is Lucas Pianigonda, and I've helped over 30 MedTech companies to be more sustainable with plastics. And here we go. Here is our 11-step framework for design for sustainability. And this is part of our holistic MedTech design module, and we're giving it away on YouTube completely for free. So let's start to go through all the steps. Then we'll go into detail for every small step. And in the end, we'll summarize. This is the plan for the video. So first of all, you should think deeply about your use case. Then you challenge your existing business model. You reduce your product to the core function. Then you reduce the number of components. You optimize these components in terms of weight and cost, of course. You optimized the packaging. You design everything for disassembly. Then you use a holistic process to make a structured material decision. For example, our Great Match frameworks exactly solves this problem. So you have a structured material selection process. And then you design for recycling, streamline your supply chain, and in the end, you calculate the environmental footprint using an LCA. You calculate, of course, also the production cost, and you check if the performance is where you want it to be. And then in the end, you will loop back and start in the beginning again. So it's an iterative design approach. Good. Moving on. So first step, you should be thinking deeply about the problem. And what so many technical peoples like we do is we fall in love with a solution. So we have cool tech, and that cool tech is our hammer. And then we run around in the world and everything looks like a nail, and we just are having a solution in search of a problem. But you should fall in love with the problem and not with the solution. Go and fall in love with one problem that you're trying to solve that is painful enough so that people will be willing to invest in you, so that they will be willing to fund this project and also in the end buy the product. Because the biggest waste would be to solve a problem nobody's actually finding painful. Good. You should go out and measure what the problem actually is. So you should not make assumptions. You should measure. Define what problem you're truly solving. Write that down. And it's super important that you go and see for yourself. There's a principle in lean manufacturing called Genbutsu, and it means like get your boots on the ground or go see for yourself. And that means that you should go visit an OR, go visit a lab, go visit your site of use for your medical device, in vitro diagnostics, or your pharmaceutical. Go and look where it is actually used and try it for yourself. Observe and question. What are the real pain points? And how is it actually done? So I have a very good example for this. It's like we had Dr. Axel Böse, who's an engineer and also working in a clinic. And he was observing this procedure that the doctor was doing. He was bending over to make a cut with a stapler. And he just asked the doctor, hey, why the hell are you like bending over like this? It's like you must have back pain doing that. And he said, yeah, the device doesn't let me turn like this, so I'll have to bend over, otherwise it doesn't work. And he's like, yeah, I'm an engineer. I can make a hinge here, and that works perfectly. So go and observe these cases because it's very obvious what you should be doing at that point. And document the constraints, the technical and the sustainability constraints, but also the user needs. Really, document what you should be solving for. And then comes step number 2. Usually your business has a business model. So maybe you sell devices or whatever you're doing. You should be throwing the book out a little and forget how we've always done it. So if you come with, we've always done it like this, that's probably not the best solution, because you should start fresh and reimagine the value that you're creating. Start with assumptions like, can we make this a service? Can we make this delivering outcomes? Can we make a device or an outcome as a service? Explore prevention models, because you could be solving the cause at the root and not the symptoms of this cause. And what I recommend is that you use the business model canvas map And those are 7 elements of a business model that you should be able to answer. If you don't know what it is, just Google business model canvas and it will pop up. That is a good tool. And you should think how you can incorporate circular models such as reuse, repair, remanufacturing, and long-term value into your business model. Good. Then what you then should be doing when you have figured out what this is for, what we're solving, what our business model is going to be, then you start to reduce the product to the core function. Make a minimal viable product that only has what it needs, and it should eliminate all bells and whistles because that avoids over-engineering. Less complexity means less cost. Less material means less footprint. Very easy. Smart design is always clear. This makes the processes easier. It makes it easier to get it approved. And you should think outside the box here. It's just how many components can we put together and the device still works? Can we reduce from 15 to 5 components, so to say? So just make it as easy as possible, as essentially only solving that problem that you identified. And what you should do here is you can explore concepts such as a very small single-use sterile component that is then contaminated and thrown away, and a bigger multi-use component that can reduce the environmental footprint significantly. Then you should reduce the components amount. So reduce the number of components, make fewer parts. That makes it easier in assembly and logistics. It saves costs in production and supply chain. And it also means that if you have plastic parts, you need to have less tooling. And an injection molding tool is very costly. So if you go from 12 components to 8 components, you save 4 injection molding tools. That's 200,000 euros right there. So that reduces cost, it reduces complexity, and it leads to stable processes and easier compliance and testing. And of course, it reduces the footprint. Good. Then, when you have these components and you have fewer components than before, you try to optimize them as much as possible. There are a lot of good software out there. So FEM or topology optimization software that removes excess material, and you put only material there where it's actually needed for the function or where it's actually seeing stress. What you can do is you can get yourself inspired by nature, because if you look at trees, they only grow wood where there's actually some stress going on. So if it looks like a natural, tree branches are very, very efficient in material use, for example. So that leads to a lower weight, easier handling, and reduce shipping costs, of course. And in general, less material means less cost and better CO2 savings. Then we move on to step number 6. We optimize the packaging, not only the product, but also the packaging. And in the very early stage, we should think about packaging, because packaging is not an add-on. It's a part of the product. And since the PPWR, it's also a part of compliance. And in terms of sustainability, the regulatory requirements are very much pushing you towards optimized and sustainable packaging. So you should design it compact and lightweight, reduce the material as much as possible, and reduce, of course, also multi-layer foils, because this makes it better recyclable. Comes again in point design for recycling. You should use either recycling or bio-based materials as much as feasible, I would say. And this all, if you optimize it as much as possible, this leads to lower costs in logistics and waste disposal in the end. And also the EPR modulation fees that are in the PPWR, they're going to be greatly reduced if you have a great sustainable recyclable packaging. What you should be taking into account here is that packaging usually isn't the biggest lever that you can pull in terms of a medical device, because the device usually is I use the analogy of a steak here. It's if you have a steak and that's wrapped in plastic, so the plastic usually doesn't have the environmental impact of the steak. The steak is the thing worthy of protection, and we use a little bit of plastic in order to protect something that is a lot more environmentally costly and also economically more costly. So if you have an implant, very expensive, very high environmental impact to produce, and then you have a packaging around it, it should make sure that you really have a sterile barrier and that this implant is safe. So we should carefully balance sterility. These are the requirements of 11607, the ISO norm for sterile packaging of medical device, with the reduction. Very important that we balance this. Then we have design for disassembly. We try to favor click joints as much as possible and avoid adhesives and welding. Then we should use fasteners that allow reuse or recycling. And we should also consider water-soluble adhesives, because that is a reversible joining method that will enable the design for disassembly. If you have higher disassemblability, it's easier to recycle. So things that you should be avoiding here is, for example, two components injection molding, where you mold something onto another component and that's not disassemblable anymore. Then, point 8, and in my opinion, this is a very, very important point. I think not the most important one. The most important one is the last one, but the second most important one, this is sustainable material selection. You should apply a structured and holistic material selection process. And of course, we recommend our Great Match framework that is part of the Great Match program. And if you're interested in that, there's a link in the description for you. But any other structured material selection process will also do the job. The idea is here to balance technical, regulatory, and sustainability requirements against each other. I would prefer to use bio-based, recycled, or downgraded options, of course, where possible. Ensure compliance to REACH rules, biocompatibility, MDR, and minimize hazardous substances. So bisphenol A or PFAS should be reduced as much as possible, since those will get under regulatory scrutiny in the future, and they're also not future-proof. They can also cause some issues with biocompatibility. And this is the next point that you should initiate. At this point, you should initiate, or depending if you have already looped once, update your biological risk assessment. You can do that by checking data sheets, by checking the formulation, see what extractable leachables and residuals can be in your plastic material. And with that, you have a quite good understanding if that material is going to be biocompatible in your final medical application. Moving on, we have design for recycling. So you should favor monomaterial designs. You should minimize inks, colors, and coatings, since those make it less likely to be mechanically recycled in a high quality. Of course, as we said, multi-layer foils are to be avoided. Same reason, difficult to mechanically recycle. And you should minimize the material variety. So if you can make everything out of polypropylene, you make it out of polypropylene. Because if everything is out of polypropylene, you can throw it in the polypropylene bin and it's going to be recycled as a pure polypropylene. If you have 15 types of plastics for 15 different components, it's probably getting a little more difficult to recycle and sort everything. And what I recommend here is that you check out our videos on recycling and medical waste. We can link that on the screen here. And then we move on to streamlining the supply chain. So number one is you should understand your supply chain. Your supply chain should identify the key materials, the key suppliers, the key component flows that go into making your medical device or your in vitro diagnostic. What you can be doing, and those are options that you could be doing. So number one is mandatory. The rest, I would say, is a little more menu and based on your analysis. So number one, what you could be doing is nearshoring and localizing. In the current geopolitical landscape, it's probably not too wild to say that it's a little unpredictable. So if you have a supplier from the US or China or wherever you have your suppliers, it's not given that the cost is going to be constant, because tariffs are thrown around very, very frequently nowadays. So if you have a nearshore supplier that is very local, you have shorter supply routes, that means lower CO2 footprint, and you have higher resilience, you are a little more flexible. And that also goes hand in hand with shifting towards low carbon regions. If you can manufacture where the energy mix is cleaner, and that gives you a better CO2 footprint. Of course, you need to balance this with cost. This is important. So cost and CO2 footprint both should go into the sustainability assessment. And then a very, very classic trick that you can pull is like bundle plastic grades. So as I said, you shouldn't have a lot of material variety, but this can also be done with the same kind of plastic. So if you have 20 different polypropylene grades, why do you have 20 polypropylene grades? And can I use 1, 2, 3 main grades that I use? Because that bundles volume and that gives you the better price. If you buy plastic as a full truck, it gives you the better price as if you buy it by the bag. And that gives you just simply economy of scale. You should optimize your logistics. So choose low carbon transportation modes and more efficient routing. As a rule of thumb, air freight is the worst. So if you fly stuff around, that has a significant impact. Cargo, so big cargo ships and train are the best transportation modes. Truck is in between, but usually the material overshadows the transportation. So avoid air freight as much as possible. Good tip here. And then the last 3 points would be in-source smartly. So where you have really critical parts and are very carbon intensive, you can control the cost and the carbon footprint better if you in-source them. Sometimes that's not the case. So it really depends on the analysis of the situation. Since manufacturing high intensity or energy intensive parts where the carbon footprint of the energy is lowest is an ideal setup. But sometimes it can make sense to in-source certain parts in order to have cost and sustainability under control. Then you should close the loop, integrate recyclers and feedstock suppliers directly in the supply chain as much as this is even possible. It depends a little bit on your setup. And then you should think about the reverse logistics. So if you're in the beginning have said, okay, we want to have a reuse system, we want to have a take back and recycling system, you should think in the design phase, how do we manage this? How do we design this service in order that the customer will in the end give us these parts back that we want in order to have the reverse logistics in place? And then 11, and this is the most important point, you should conduct a life cycle assessment. You should start with a very simple estimate, materials, energy used, and the CO2 footprints of the energy usage and the materials. You can take into account transportation, but keep it very, very simple. And then refine as you go. You start with, okay, we have this much material, we have this CO2 footprint for the material, and we have an estimation of the process energy. And that's good enough. And then as you loop through this again and again, you will build the LCA. You will start to refine it as you see fit and as you understand more and more where the biggest levers are. At this point, I would recommend that you check out the podcast with Thomas Kegi. You should see that video linked in here. And he's an expert on LCA and he holds university level lectures on LCA. So check that really out. He's very pragmatic also. And as we do an LCA and we loop through this iterative holistic design approach, we will update every time our LCA and check the environmental footprint, check the cost calculation, check the performance. So we build our device and here we measure and we learn from this. So this is the lean startup methodology, build, measure, learn, make an MVP, you measure. This is the measuring step. So this is the most important one in my opinion. And then you learn from it and apply it again. So you loop back again. So from number 1 to number 10 is built and then number 11 is measure and then you go back and you learn again and you apply it again. So this is our framework of designing for sustainability. Of course, there's a lot more to this in medical device development, but this is the gist. And if you want to design your devices for more sustainability, there's a link in the description for you. And if you like the video, like, comment, and subscribe because YouTube will show you more of our stuff, more similar content. It's because of you and not because it helps me. Of course, it helps me. If you have a question or you want to request a video, write comments below because I read all the comments and I answer all the comments if I can. And I try to bring value to you. So tell me what you want from me and I'll make these videos. So thank you very much for watching and until the next time.